Hello class. So today what we're going to do is we're going to just kind of recap the Unit 11 Day 1 notes. We took these on the last time that I saw you on that Friday the 13th. If you weren't here on that day, the notes are posted on Canvas. I believe everybody in this class got a copy of the Unit 11 packet, but I know a handful of you were gone on that Friday. But hopefully this will help if you kind of already looked at the notes and maybe didn't understand all of it. I'm just going to kind of go through it real quick, and then I'm going to do a little bit of the Day 2 notes. We're going to kind of skip a majority of the Day 2 notes, but we'll do a few key things. So going to the Day 1 notes, what we did a while ago was we talked about circles. Circles are named by their center. The center is always going to have a capital letter by it. So like this would be circle A. When it comes to the parts with circles and segments and things, a chord is going to be a segment whose endpoints are on the circle. So it will be a segment, not a line. And it'll go something like DL or TO or TD. Those are all chords. The ends of the segment are on the circle. Diameter is going to be a chord, but it cuts the circle in half. It goes through the center. So it's going to be like this, DL, right there. A radius is going to go from the center to a point on the circle. So something like ID, IE, IL. Again, those are all segments, and they are going to be exactly half of the diameter. A secant and a tangent, those remember were lines. So they're going to have arrows on the ends. A secant is a line that crosses a circle in two places. So this line here, you'll notice, crosses the circle in two places, D and T. So this is a secant line. It's called line DT or TD. Either order is fine. And notice we use the line symbol. A tangent is going to be a line that crosses a circle only in one spot. And it also has to have arrows. So this would be our tangent line, LZ. Where that line intersects the circle is going to be the point of tangency. It's where the tangent line intersects the circle. And then we talked about all kinds of arcs. All right, a central angle is going to be an angle whose vertex is the center of the circle. So like this angle here, AZB, that's a central angle. When you have a central angle where the vertex is the center, the angle will equal the arc. So this angle, AZB here, will equal this green arc. And the arcs are noted with like this kind of arching symbol here, arc AB. An arc is just going to be any kind of unbroken part of the circle. So arc AB would be an example of an arc. There's different types of arcs depending on their sizes. There's minor arcs, and that's going to be an arc that is smaller than half the circle. So like arc AB would be a minor arc. Arc AC would be a minor arc. You're going to always use two letters to define it, and don't forget the little arc symbol. A major arc is going to be an arc that is more than half the circle, and when you name a major arc you have to use three letters. So looking at like this yellow arc down here, you'll see that that's obviously more than half the circle. You wouldn't want to call it arc ED, because if you only use two letters you go the shortest distance, and that would not be more than half the circle. You have to use three letters, so, and go in the order in which you would draw it. So like arc EFD or arc DFE, something like that would be good. And then a semicircle is going to be exactly half of the circle. And again, you're going to want to use three letters to define that if possible. So like this purple arc here would be arc DEF or arc FED. Make sure you go in order. So those are the different types of arcs. And then we did the arc addition postulate, which we've already done this kind of stuff with segments and angles before. It just basically says these two little arcs, the yellow and the blue arc, they add up to equal the purple arc. And hopefully that kind of makes sense. If you're walking from A to C, you're going to have to count how much A to B is and how much B to C is, and then add them together. And then we did a whole bunch of examples. And just things to kind of keep in mind. If they tell you circle T, we know that T is the center. And so something like DZ would be a diameter. And that comes in handy when you're looking at something like this green arc here. That would mean that that arc has to be 180 degrees. Same thing with this other arc over here, D to Z over here, DOZ. That arc would also be 180. So those are helpful. Other things to keep in mind are like vertical angles. So like this angle here is 48, and so that angle there is also 48. And using the theorem on the other side, if you have a central angle, so like this is a central angle because the vertex is the center, the angle will equal the arc. So because this angle is 48, we know this arc is 48. And because this angle is 48, the arc that it opens up to is also going to be 48. So that's kind of helpful in finding different things. Yeah, and let's see, for this one, like to start this problem to find x, we use the arc addition postulate. So we had DE, we had EL, and we were given DL. So we knew this piece, DE, we knew this piece, EL, and then we knew the whole thing, DL. What we did was we took DE plus EL and set it equal to the big piece, DL. All right, so DE, 3x plus 15, plus EL equals DL. All right, these two arcs add up to equal this big arc DL. And then we solved for x and we got 11. And then once we found out 11, we were able to kind of look at certain pieces of the circle to find the missing arcs and angles. And we did that down here as well. All right, so same kind of idea. We started off with BI, IG, and GL. BI, IG, and GL. We were given this arc, and this arc. And if you notice, if you put all three of those arcs together, you get half of a circle, which would be 180 degrees. So that's what we did. We added those three arcs up and we set it equal to 180 degrees, and we were able to find x. And then after that, we kind of utilized different things like the fact that this is a 180 degree arc, or the angles equal the arcs. So like this angle will equal this arc. This angle will equal this arc, and vice versa. So we were able to find different pieces that way. And then down here we just kind of utilized some of the vocab. So a diameter again is a segment. It cuts the circle in half. It goes through the center. It's a chord. So like BA or AB. Chords are going to be segments whose endpoints are on the circle. So like EB, BA, RA, and again they're all segments. Tangent is a line that intersects the circle in one spot. So this has arrows on it and it crosses the circle in one spot. So EZ with the line symbol. Radii, a radius, would be from the center to a point on the circle. So SB and SA, and they're segments. And then a secant is going to be a line. So it's got arrows and it's going to cross the circle in two spots. So AR. All right, so yeah, hopefully you guys were okay with that material. I know it's been a while. We'll review again in a few days this stuff. So we'll do some specific examples in a few days so that you guys can kind of see how that works. But what I want to do real quick is I want to go to the day 2 notes. I said at the beginning of this video that we weren't going to do most of these notes just because I don't think they're super important. I'd rather focus on what is important. But a couple things that I did want to focus on are this guy right here, all right, congruent arcs. In congruent arcs, we know what those are. It's two or more arcs that have the same measure. All right, but the main thing that I wanted to focus on is in a circle or congruent circles, if two arcs are congruent, then their central angle and chord are also congruent. Okay, so what I mean by this is if let's say we knew that arc TI was congruent to arc GE. All right, let's say that we know that arc TI, oops, I did the wrong symbol, arc, not segment. All right, so arc TI was congruent to arc GE. If those arcs are congruent, the segments that open up to those arcs are going to be congruent. So this segment TI and this segment GE, those will be congruent. TI will be congruent to GE. and their central angles. The angles that have a vertex at the center and open up to those arcs or segments are going to be congruent. So angle TRI will be congruent to angle GRE. All right, so for example, in this example, these two arcs are congruent, which means that the chords that open up to those two arcs are also going to be congruent. So x squared minus 5x has to be equal to this guy, 20 minus 6x. And from there you would have to solve it. Because it's an x squared, you'd have to factor it, make it equal to 0. So I'm going to bring the 6x over and bring the 20 over as well. So you end up with x squared, you'll have plus x minus 20 equals 0. And then you got to factor it. Two numbers that multiply to be negative 20 and add to be 1 are going to be x plus 5 and x minus 4. 5 times negative 4 is negative 20. 5 plus negative 4 is 1. Set them equal to 0, you get x equals negative 5 and x equals 4. From there, you want to plug it in and make sure that it works. Remember, if you plug it in and it makes something negative, like a segment or an angle negative, that's a big no-no. When you plug in 4, you're going to get 20 minus 24, which means that this would be negative 4. That doesn't work. If you plug in negative 5 will work. You would get 20 minus negative 30, which is 50, and you would get 25 plus 25, which is 50. So the only one that actually ends up working is the negative 5. And then same thing with number 2 here. If TA is an angle bisector, we know that this angle and this angle are congruent because it's being bisected. And if those angles are congruent, that means that these arcs are congruent. So you would set 2x minus 113 equal to 2/3 x plus 7. And then you would go ahead and solve from there. And you would get x equals 90. All right, so that's an important theorem I wanted you to be aware of. And then the other one that I wanted to kind of just bring to your attention is if you have two tangents, segments that are drawn from the same external point, then the segments are congruent. All right, so remember a tangent, technically as a tangent, it would kind of keep going, but this is a tangent, all right, it's going to cross the circle or touch the circle in one spot, and this is a tangent. If they are drawn from the same point, they're going to be congruent to each other. So if you have something like number 6, you're going to set these two tangents equal to each other. So you would set x squared plus x equal to 12 minus 3x. In this one, you would set 3x minus 55 equal to x over 4. We're not really going to do one like number 8, but I just wanted to kind of show you the basics. If you have two tangents drawn to the same circle, you can set them equal to each other. They're going to be congruent. All right, so that is kind of a quick little recap of day 1 and a little bit of new stuff from day 2. There's a Canvas quiz for you to take on the Canvas page, so go ahead and give that a try, and I will talk to you soon. Thanks.